you guys are aware of. We've got acid-base reactions. What other types of reaction classes do we have? We've got substitution. And isn't that fun? Just within the class of substitution, we have two different types. We get the SN1 and SN2. What other reaction class do we have? We've got our eliminations. What's irritating about the eliminations as well? You get E1 and E2. And our last reaction type, I think last one, addition. Okay, which is what we saw in chapter 5. Okay, I think we only really get one type of reaction when we're looking at addition. Okay, or at least one class that we're going to separate it based on. There are other types of reactions. You can get free radical reactions. Thankfully, we don't have to worry about them this semester. Anybody remember any other types? I think it's just these four. I almost always seem to forget one somewhere along the lines. Okay. Chapter 8, and then our carbonyls and our arenes, particularly the carbonyls, take a mix of all of these different substitutions or different types of reactions and puts it into one reaction. So when I do a reaction between water and a carbonyl, I do some acid-base chemistry, I do some substitution chemistry, I do some elimination chemistry, technically do some addition chemistry as well. Okay? So each mechanistic step, when you move to the more complex functional groups, can be classed according to these different reaction types. So being able to identify the reaction types becomes exceedingly important. Okay? So you will get tested on that for the rest of these exams. Okay? So on that bright, happy note, let's go through and finish up chapter 5, okay, as far as the alkene reactivity goes. Okay? So there's some things that I forgot to include. The syn and anti-addition, that slide is now posted, though at the same time I forgot to mention the redox reactions. So our syn versus anti, as we spent a little bit of time talking about on Monday, we're ultimately just looking at the same thing, we're just calling it different because our perspective is slightly different. It's the action versus the result. Okay? But they're ultimately referring to the same thing. So a syn addition corresponds to cis, and the anti corresponds to trans. Okay, so there's pair up. We might as well draw on that too. So our cis and syn are similar, and our trans and anti are similar. Depending on the situation, we may have a trans or an anti-addition that doesn't produce trans products. Okay? So it just depends on the different circumstances on what you're trying to do. Okay? They effectively are referring to the same general idea, just depends on your results. Okay? The other big thing that I forgot to mention when it came to redox reactions. Okay? There's a lot of there's at least one homework problem that goes through redox reactions. And the types of problems that you will see kind of range all over the place because it's the textbook and it's just what they assign. As far as I'm concerned, for questions that I would ask, they're going to boil down to these two simple definitions. Okay? A reduction reaction is a loss of oxygen bonds. Okay? Or a gain of hydrogen bonds, depending on the situation. Okay? That reaction would get classified as a reduction. An oxidation reaction is a gain of oxygen bonds or a loss of hydrogen bonds. Okay? So they're interplay with each other. Certain circumstances, the definitions work better than in others. Okay? So a couple big examples that we could go through here. If I started with, and this will happen when we move into the alcohol chapter, if I start with the alcohol and I convert it into a ketone, what type of reaction occurred? So, go through and identify our definitions. Okay, we're looking at an oxidation reaction. I gained oxygen bonds. I started with one oxygen bond, I now have two. Okay, the other option was looking at the hydrogen. I lost hydrogen bonds. You'll notice the hydrogen attached to the oxygen is no longer there, and What other hydrogen disappeared? Off of our carbon. We lost that hydrogen as well in this reaction. Okay? What if we'd reverse the reaction? Instead of going from left to right, everybody's least favorite, now let's go right to left. What type of reaction do I do there? Now it's a reduction, okay? Because I gained hydrogen bonds or I lost oxygen bonds. So when we're referring to redox reactions, as you might remember from Gen Chem, it's almost always referred to as redox because they're paired. If you get one thing being reduced, another one's being oxidized. So if we look at a oxidation from left to right, if we reverse the reaction, it's going to have to be the opposite, a reduction. Okay? One more example of this. We erase those, and let's take a look at what functional group is this? It's an alkene. And we take it to this guy. Did I change the number of oxygen bonds? No. Okay, does that mean it can't be redox? No. Instead, what we'll do is look at our hydrogens. What happened is we went from left to right. We gained hydrogen, so what type of reaction is this? It's a reduction. How else could we refer to this reaction? Yeah, I heard it there. We added that hydrogen that we started with. We did an addition reaction. So we could call this an addition reaction or an addition reduction reaction, some combination thereof. Okay? How are those hydrogens added to the double bond? Same side, also known as what kind of an addition? A syn addition. Okay? Just throwing it all together there. Okay? Questions about that? Okay. Like I said, the homework will have you do some other ones. Consistently, I've noticed across the board for almost any instructor I've talked to can run into questions or problems that they end up getting confused on as whether it's reduction or oxidation, which means I will stick to the simple examples, the ones we just kind of talked about. Okay? Questions about that? Okay, so if you run into problems with the homework, you might just send me an email asking just to make sure that something else isn't going on. Give me a second here. Let's quit. Otherwise, I'll assume you guys are comfortable with it and we can just kind of move on from there. Okay, I'll try and throw on the next quiz some redox reactions, and we'll see them in Chapter 8. Okay. So some examples of redox reactions. We just looked at one, hydrogen. When we added hydrogen to the double bond, and we just set our answer, we get the syn addition. Referring to this as a cis product. Does it make sense to refer to that product as a cis product? Okay, what's on the same side though? When we refer to cis and trans, typically what are we referring to? Two groups other than hydrogen. What are the two groups other than hydrogen on that ring? There aren't any. Okay? So if we called that a cis product, we'd get funny looks because there isn't really anything to be cis or on opposite sides of. We'd have to say that it's the hydrogens are cis from each other. The added hydrogens were cis of each other. Okay, so we end up getting really specific and referring to it as a cis product. That's where it gets a bit odd. Okay. The oxidation, so that was a reduction reaction. We do have an oxidation reaction as well. Okay, so this one was a reduction. We could look at the oxidation with the osmium tetroxide. Okay, and then followed by the next one as the second step of this. So we would typically see this labeled as step 1 and step 2 written right underneath it. Sodium HSO3. Okay. What happens in this case? We're doing again an addition reaction. The result is we've added 2 alcohols, so we produce a diol product. Okay. Further, those alcohols in the product are in what relationship? Cis. So we could look at this as a cis diol. We could also refer to it as a syn addition. Okay? You're not responsible for this mechanism. You're responsible for knowing that you generate the diol from the alkene and that the alcohols are added in such a way that they are on the same side of the ring. Okay? Let's see. I was hoping I added another slide here. Shoot, it's not there. There is another way to do this reaction. Okay? It's a little bit more common because it's a little bit less dangerous. Instead of using osmium tetroxide, sorry, I really did think I had this on a slide. We can go all the way over to our diol using a different reagent. Those of you in lab, what reagent? Pulls at the memory strings, I'm sure. Exactly right. KMNO4. Typically you'll see it written out as cold and dilute. Why would we add cold and dilute? Because when it's hot and concentrated, we get a different product. Okay? You change the temperature, the structure falls apart differently. Okay? So we get 2 possible reagents that we could use to make this cis diol. You can use potassium permanganate or you can use the osmium tetroxide mess. Okay? Just because you didn't have enough stuff to remember. Okay? So now what we're going to do is move into yet another pseudo-functional group. This one is difficult to kind of process, particularly because a lot of people had problems with the bromonium ion, that 3-membered bromine ring, okay, with the carbons in the bromine. Guess what we generate in this case? Now instead of bromine being in the ring, what do we have? We have an oxygen. Okay? So it's a question of how do we get that oxygen in there. When we reacted and did the bromine was large enough that it could kind of insert itself in between, and it allowed for that functionality to occur pretty quickly. Oxygen's a little too small for that to happen really easily. It's also a lot more reactive. So getting a hold of oxygen to be able to slide it in there is not the easiest thing to do. And we can't just add elemental oxygen because that's now super stable for other reasons that we don't need to address. So we need to come up with some way that we can make the oxygen reactive enough to insert itself. Okay? And so to do that, we're going to kind of mimic what we would expect from the bromine. So when we looked at bromine, it was Br, a single bond between the 2 bromines. If we looked at elemental oxygen, how many bonds are there between elemental oxygens? 2. Yet another reason why the oxygen in its elemental state isn't going to be as easy to work with. Okay? So we're going to kind of mimic the bromine addition by making sure we've got a single bond between our oxygens. Okay? Like I said, that's not particularly stable, so we have to add some other pieces to help stabilize it. Okay? That ends up being a really reactive functional group. In fact, that bond ends up being exceedingly reactive. Okay? Because the oxygens don't want to share their electrons with all those different groups. Okay? Anybody know what type of bond that is? Seen it before, maybe? Ring any bells? No nurses having to clean wounds or anything like that? Peroxide. What we're looking at is a peroxy compound. Okay? So the peroxy is referring to that red bond. The most common reagent used, that R group. So what does that R stand for? What does R stand for in general? Or in Sargent? Can be pretty much anything we want it to be. The most common source for this is making that a benzene ring. Now our compound is referred to as a peroxy benzoic acid. Not particularly easy to write, so one of the things we end up condensing this to is PBA. Okay. We can make this further reactive to make sure we get this set up correctly by attaching a chlorine out here. That chlorine, we'll talk about it when we talk about the arenes, is in the meta position on the double bond. So we've technically got a chloro peroxy benzoic acid. The reagent name condenses down to mccPBA. Okay, I can barely write out, as you can clearly tell, metachloroperoxybenzoic acid. Not even necessarily in a straight line, but even in the same dimension, which means what would you expect to see on an exam as far as a reagent? You'll see it condensed to mccPBA. Okay? If you see that, you should be thinking of forming the epoxide. Okay? mccPBA will react with alkenes to form the epoxide functional group. What ended up changing in this case? We took the electrons in our double bond, we shared them with oxygen, and then our oxygen shared electrons back to the other carbon in our double bond. Okay? So we end up losing the double bond by shifting those electrons out into a sigma bond with oxygen. Okay, you guys kind of see that? Yes or no? Okay, all we're trying to, and I'm about to show the mechanism which may or may not help with that. Okay, so let's kind of piece together the electron flow for how this is going to occur. Okay, so ultimately what you're going to be responsible for, because this mechanism is a bit of a beast, is recognizing that if you see mccPBA in an alkene, you should immediately draw the epoxide shape. Okay, so what happens if I gave you this and then said mccPBA? What's the product? What's that? Okay, the epoxide tells me the functional group. Give me a little bit more information than that. So I've got the ring. Is that my answer? What am I missing from that? Okay, so the mccPBA is the one that brings in the oxygen. So there's the oxygen. What are these? Carbons. Where did the carbons come from? This reactant. That one was a bit obnoxious because I abbreviated it. Really, that's... How many carbons would I expect in my product? 2. There's my 2 carbons. Okay? I only see 2 bonds to these carbons. So what does that mean? There's implied 2 hydrogens. How many hydrogens did I start with? 2. What's the answer to this? That's it. Okay? What happens if I now draw on this structure? Ooh, it'd be extra fun. Let's put that. What's the answer now? Good answer. The exact same structure, except now we've got that other big freaking junk of a piece that I probably can't replicate actually drawing. So it was a bad decision to draw. 1, 2, 3, 4. 2, 3, whoops. 3, 4. What did I say? This? Crap. I can't even draw it. Okay? So the mccPBA only reacts with the alkene. At this point, that's all I want you to recognize. Anything else doesn't react, which means you draw it in your product. Okay? Does that kind of make sense? Okay. So let's erase all of those and get really excited with this mechanism. I can feel the excitement raging for this mechanism. Okay? Where's going to be a good place to start? What do you know about the peroxy functional group? How many problems have you worked with a peroxy functional group? Probably 0, or you might say 1 because we just did 1. How many problems have you worked with an alkene functional group? In theory, you should have at least done the quiz, which had 4 or 5 problems on it. So if we had to pick a place to start, which functional group should we start with? Alkene. The alkene. What does the alkene supply? We've got those pi electrons. Those electrons need to come out and somehow react with an oxygen. Which oxygen do we want to pick, assuming I'm nice as far as I've prepared this? Okay, one that's most reactive, but you don't know much about the peroxy, so that's going to be a bit dangerous. That's why I added the assume I'm nice about this. How about the oxygen that's closest to the double bond? Okay, so let's take those electrons and let's share them with that oxygen. How many electrons did oxygen have around it before that bond, or before that occurred? 4. So if I take those electrons and share them with the oxygen now has how many electrons around it? Would have it started with how many electrons around it? 4 pairs of electrons. We just added another pair, so we've got 5 pairs, which is 10 electrons. How many electrons can oxygen have around it? 8, or 4 pairs, which means we have to break a bond. Too many electrons are around this oxygen. Which bond do we decide to break? Okay, we've got 2 options. We can either break the oxygen-oxygen or the oxygen-hydrogen. Whichever we do, the electrons in that bond must go with that atom. So let's say it's with the hydrogen. Would I expect hydrogen to take electrons away from the oxygen? No, why not? Difference in electronegativity. That step doesn't make physical sense. So we'll erase that. Okay. So let's go to the other one. We'll take those electrons and we could put them onto oxygen, but we're going to be a bit adventurous and we're going to push them over to that bond. How many bonds would this carbon now have? 5. Can carbon have 5 bonds? No. So that's not a particularly good thing. So we need to break a bond. Which bond do we decide to break? The pi bond that's there. Why? The easiest bond to break. Our other choices are the pi bond we just formed or sigma bonds with the R group. Pi bonds are easier to break. So let's take those electrons and we want to find some place to stabilize those electrons. So we want to find something relatively positive to stabilize them on. Okay? We could try and shift them to the oxygen that's right next door. But is that oxygen particularly positive? No. Is there something that's more positive nearby? It's the hydrogen. Good call. How many bonds does that hydrogen now have? 2. So we're going to have to break a bond. Okay? These, I didn't like my first arrow. I'm going to adjust that real quickly. It's still the pi bond. We'll come back to why I'm changing it in this very step. Okay? So that hydrogen now has too many electrons, so I'm going to have to take these electrons and move them somewhere that can accept them. Oxygen could accept them, but it's also not particularly positive. Is there anything else that's positive nearby? The carbon right here. So what we can do is take those electrons and push them down. Okay? So let me color in the bonds forming our epoxide. We're taking our electrons from our pi bond out to that oxygen, push a bunch of electrons through the peroxybenzoic acid, and then we take our electrons here and shift them in. Whoops, I wanted those in green, just so they stood out as a different color. So if we go to look at our epoxide, we could make the statement that this bond, that visible, is our blue electrons, and that the bottom one is the green electrons. Okay? Do you see those pieces now? Is that a little bit easier to see how that reaction occurred? You notice we've got a lot of arrows moving through there, and they're doing kind of weird, goofy things. Okay? So it's not one that I would expect you to memorize. Okay? But I do expect you to be able to push those arrows. So if I drew that structure for you, all those arrows, and said provide the product, you should be able to provide the product. Because I'm telling you where the electrons are moving. You have to do that motion and draw the product from that. Does that make sense? Okay. So now what we're going to do is make this even worse. Okay? Okay? We're going to evaluate the reactivity of that epoxide. Okay? It's a three-membered ring, so what bond angle do we get within that? Again, effectively an equilateral triangle. 60 degrees. What's the hybridization of all three atoms in the epoxide? sp3. I will leave that to you to make sure you can prove to yourself, which means all of three of those atoms want to have what bond angle? 109.5. We are forcing them to be 60 degrees. What does that mean about the energy of that ring? High or low? High. I'm forcing a lot of electron density into the same area. So that ring is extremely stressed and it wants to break open. Okay, so that's what makes the epoxides fun chemistry. Okay, so what can we do with that? Let's see. Oh no. Oh man. Stupid computer freezing. So what we can go through and do is now react these epoxide rings with a nucleophile. Okay? So what can you tell me about a nucleophile? What's that? Nucleophile we would typically draw with a lone pair. We might even mark it as a negative charge. Where would that nucleophile react with the epoxide? What would it need to react with? A positive or a negative? Positive. What atom is positive within the epoxide? What's that?
Hydrogen.
Which hydrogen? Okay, so we could add, we do have hydrogens out here. Are those hydrogens particularly positive? For a hydrogen to be positive, what does it need to be bound to? An electronegative element, right? What atom are those hydrogens bound to? Carbon. Is carbon that much more electronegative than hydrogen? No. And if we think back to the very beginning when I told you to be able to classify different bonds, what kind of a bond is a carbon-hydrogen bond? Covalent, which means equal sharing of electrons, no charges. So while hydrogen in general might be a good idea to match up with a negative, not so in this case. So try again. Okay? This carbon right here. That carbon is bound to two hydrogens, which we just said were covalent bonds, which means equal sharing of electrons, so it's not very negative there. And now it's bound to two carbons, carbon to carbon bond. That is what type of a bond? Covalent, also not very negative or positive. Huh. There we go. What other carbon? How about the one that's bound to an electronegative element? Okay, our oxygens. Okay, is that the carbon you guys were referring to, the ones I've tagged as green now? Why did you guys not look at the red ones? Okay? You guys are already doing the first step of all organic chemistry. You're already ignoring and shifting stuff out that you don't think is important to analyze. Okay? So that's a good first thing to do. And then you try and move on to the next step, and you end up bringing in those other things and making them do other chemistry. Okay? So focus where the chemistry, where you think it's going to occur. Start to identify charges. What charge should those green atoms be? Partially positive. So what we're going to do is have our nucleophile come in and share its electrons with that partially positive carbon atom. How many bonds does that carbon atom have right now? 4. If I bring in electrons from the nucleophile, how many bonds would it have? 5. Can carbon have 5 bonds? No. So what has to happen? We have to break a bond. What bond do we break? Why do we break the carbon-oxygen bond? So we could look at hydrogen not being able to take the electrons away from carbon. Why can hydrogen not take the electrons? It's less electronegative. Why do the carbons not take the electrons? No, why don't we have the other carbons? Say this one. What's the difference in electronegativity between carbon and carbon? Nothing. So the same reason why the hydrogen wouldn't take it, the carbon won't take it. Our oxygen is the one that's going to take those electrons because it is more electronegative. Okay? It's already polarizing that structure. It's already taking those electrons away. Okay? So when we're doing these mechanisms, we're trying to follow the natural flow of the electrons, okay, as best we can. How do we find the natural flow of electrons? What definition do you need to know, or relationship do you need to know between each of your atoms? The electronegativity. Okay? When electronegativity fails, what should you move to? Size. When size fails, what should you move to? Resonance. Okay? These same 3 questions you should be asking yourself every single time you even attempt to move an arrow. Okay? Don't ask after you started to draw something. Okay? Ask as you're drawing the arrow. Where am I going to put these electrons? Okay? And in the process of doing that, what happens to our ring? It breaks open. Where would the oxygen be bound? Top carbon or bottom carbon? Why the bottom one? Because I broke the top one. What's at the top one? Hydrogen's there. I can accept that. What else is up there? Take a look at our now black arrow. We've got the nucleophile. Every time you're showing a pair of electrons move with an arrow, you're showing electrons move. If you're starting from an atom and aiming it at an atom, you're making a bond. If you're taking a pair of electrons from a bond and moving it to an atom, you've now turned them into a lone pair of electrons. Okay? So the idea is once you pick up how to use mechanisms, you can start to predict a lot of chemistry without knowing what's actually occurring. Okay? So it's kind of fun. Okay? It still takes practice. Yes?
Is that oxygen negatively charged?
And in this case, that oxygen started neutral, gained electrons. It should be negatively charged. Exactly right. We'll go through some of that in a second. Okay? All we're trying to look at is the possibilities here. In this case, why would that oxygen be negative? Because the oxygen would rather be negative than the nucleophile starting material. Because we've got a negative on both sides of the reactions. One's on the nucleophile, one's on the oxygen. Okay? So what we've established here as far as this reaction goes is most of the chemistry. Where's going to be another problem with this? Is there anything special about those carbons in the product there? Now I'll highlight them as red. True. So I could get 2 products in this. What was that? Either of those carbons. Both of them have the same issue. Everybody's favorite chapter. Chapter 6. Those two carbons are chiral. They're stereocenters. If they're stereocenters, what do you need to specify? You need to be aware of the wedges and dashes. Where are those wedges and dashes first going to show up? They're going to show up from the epoxide. If we take a look at the bonds between the carbon and the oxygen, sorry, I'm going to erase all of that so we can see it. Would I expect those? Could I be wedged and dashed? No, it's too small. They must both be on the same side. Where's the nucleophile going to come in from? It must come in from a backside attack, just like with the bromine addition. Which means if I move to the product, if I draw my oxygen being wedged, the nucleophile must be dashed. If I was going to refer to the addition of the nucleophile and the oxygen across the double bond, what type of addition did we do? So you got the right idea. They're trans products, which would mean what type of addition? We get the anti-addition. Okay? Kind of makes sense as far as how each of these pieces move through.
So would that be a problem? Like you wouldn't put the wedges in, you would have to specify?
You would have to specify, depending on what was asked. If I asked you to provide the product, you would have to put in the wedges and the dashes. If you didn't know, so this is another big thing. Stereochemistry is a secondary feature of nearly all your reactions. Okay? You should, in theory, be able to predict that one bond becomes an oxygen, the other one is the nucleophile. So one very easy way to get at least some credit for this problem would be to specify nucleophile, oxygen. Notice no wedges and dashes. You've still specified that you understand what chemistry is going to occur, you just don't know how it's going to occur. Okay? So when you're asked to provide products, usually I'm looking for two different things. Do you know what the overall result is, and do you know how it occurs? The how is ultimately the mechanism, or remembering how that addition works, what the result is at the end. Okay? Kind of makes sense? So when you go through and do an exam, put down your gut instinct first response answer for it. If you get time, come back through and say, I've got a chiral center there. That means I should be concerned about wedges and dashes. Reevaluate the problem. Okay, makes sense? Okay, yes.
Would you also want us to indicate like the plus minus?
How many different products are produced is necessary in this too. Yep. So that epoxide could form either from the top or the bottom. For our intermediate, we don't see a difference, but we could see multiple products come out of an epoxide reaction. We could get upwards of 4 products from a single reaction.
So it would be easy to indicate
You should be indicating that because that is a result of that reaction. Okay? So I'm pretty sure the next few slides, oh man, make this actually look a little bit neater. Okay? So there's 2 different conditions under which we can go through and do this ring opening, the epoxide ring opening. Okay? So it comes down to the nucleophile we add. You'll notice that in this structure I've added some dashes. I've changed the compound a little bit so that we can evaluate a little bit more about the chemistry. Okay, so there's a methyl there that's dashed, which means the alcohol or the epoxide bonds would be wedged. If I'm under neutral or Baisk conditions, probably can't see that, but look at your slides. We'll run under what would be a pseudo SN2. Okay? Why SN2? Our nucleophile is going to come in from the back side, and it's going to come in such a way that we don't weaken the bonds of the epoxide. Okay? So we have to force the ring to break open with the nucleophile, which means we'll add a strong nucleophile or basic conditions. So a lot of negative charge. In those cases, with an SN2 type substitution, we're getting the backside attack. Which carbon would react? Top carbon with the methyl group, bottom carbon with the hydrogen. The bottom one with the hydrogen, because it has the least amount of steric. So under basic conditions, my nucleophile, oh crap, put it on backwards. The nucleophile is going to come in and attack the bottom one, where our alcohol will end up being on our product. So copy and paste sucks. Okay, so let's draw that out again. We'll keep our OH, keep the methyl group there, and our nucleophile comes in from the bottom on the bottom carbon. Okay, can you guys see that? Do I need to draw that again? Okay. What happens under acidic conditions? Acidic means we're supplying what? Be more specific, it's not just hydrogen. Hydrogen ion or H+. H+ is going to react with what? The oxygen, because the oxygen is partially negative. If I put a hydrogen on there, that oxygen becomes positively charged. What have I generated? A wicked good leaving group, which means these bonds start to weaken premature, and I run under SN1 conditions. Now where does the nucleophile attack? Under the top one, or the hydrogen, or sorry, our methyl side or our hydrogen side. Under SN1 conditions, what do we want for our substrate? Our tertiary as opposed to our secondary. The nucleophile comes in on the sterically blocked side. And when we look at our product, the nucleophile comes in next to the methyl. Okay? Do it again. What the hell? Okay? Questions about that? What was wrong with the one I just scribbled out? The nucleophile came in from the same side as our leaving group leaving. Doesn't work. It still has to be backside attack. Okay? Kind of makes sense? Okay. I am pretty sure, in fact now I'm positive, that these next slides go through and break down the mechanism. Okay? So get much more specific with what is happening on these. Okay, this is why we're seeing this with the SN1. Okay, actually why the other product was right, sorry. Once we acidify, we make that a really good leaving group. That leaving group leaves. You'll notice it never leaves the entire structure, it just leaves our reactive carbon. Why does the top bond break and not the bottom one? So why do we break red and not blue? The red bond breaks, and what do we form? Carbocation. What kind of carbocation? Tertiary. If we broke the blue bond, what kind of carbocation would we have produced? We would have had a secondary. Which is more stable? Which bond do we break? Red or blue? Red. Okay? Once we've got that carbocation, our nucleophile can then come in and attack either from the top or the bottom. Whenever you see the carbocation, you should be expecting two products, because that p orbital is empty. I can put electrons either into the top of that p orbital or from the bottom. which means 2 products. Okay? And that's what we're showing up here. Kind of makes sense? So we kind of slowed down that mechanism into individual steps. What happens if we go through and do a base catalyzed ring opening? Okay? Under these conditions, we don't have a good leaving group, which means I have to force the leaving group to leave, which means the nucleophile comes in and attacks at the exact same time as the oxygen is kicked off, which means we maintain the stereochemistry or the relationship between our nucleophile and our oxygen in our final product. Okay? If we look at a slightly different view, we can rotate our initial structure so that we can see our epoxide being above or wedged above the ring. Our nucleophile needs to come in and attack at the exact same time as our leaving group leaves. If we go through and again color our bonds, red versus blue, why would I prefer the red over the blue? There it is. There's less steric hindrance around the red. So the nucleophile prefers to come in at our less sterically hindered site. And we end up generating a different product. Okay? Where do we end up picking up the hydrogen to make it an alcohol? Okay? It's a bit difficult to exactly say where that comes from because we're under basic conditions, so we don't really have anything acidic enough to protonate it. Usually whenever we run through a reaction, we do something called a workup, where we add our reaction mixture to something like water or some other species to neutralize reactive species, like that negatively charged oxygen. Okay? So where it strictly comes from isn't super important to me. If you really want to care about it, we can go through some examples of that outside of class. Okay? Questions about your epoxides? Okay? So kind of similar chemistry to the bromine or the bromonium ion, except that we can vary that nucleophile a little bit more easily. Okay? Questions about it? Let a no. Okay, we'll go ahead and drop that as a no. So now, probably one of my favorite kind of slides. I like to call this spider chemistry. Okay. This is now posted as an actual image file to Canvas. Yeah, everybody's mouth should kind of drop with this. There is a reaction summary folder. Because I've got a little bit more time this semester, what I'm going to go through and do is for each functional group, I'm going to summarize all of the reactions in this kind of spider format, okay, and post that as an image file there. I've also got a document file that goes through and lists. For an alkene, what reagents does it react with? If it reacts with HBr, what does it produce? Okay, and I'll get that posted by the end of the week as well, okay, because that one's a little bit more complete, okay, with all your functional groups. Okay, so what we've just gone through and covered is now acids reacting with our Bronsted bases, where our nucleophile was what, for example? Anybody? Chlorine, bromine, last one, water. Okay. This generic nucleophile statement covers all of those. So we're looking at our alkene reacting as a Bronsted-Lowry base with our hydrogen to generate the carbocation intermediate. That cation can then react with the nucleophile and we get our product. Okay? You'll notice I've also added some extra information in there saying how many products you get. In this first case, or the reaction starting material that I've picked here, we really only get one product because there's no difference between the two possible products. With that carbocation, you either get the nucleophile attacking from the top or the bottom. So if I add some stereochemistry to this structure, for instance, put a dash out there, like in, say, the homework assignment or the quiz, you get two products because the bromine can either come in wedged or dashed with respect to that dashed methyl group. Okay? So this spidering is supposed to help summarize all of the chemistry that you've seen for alkenes. So there's our acid reactions. The mccPBA, I know I've got kind of organized second here, but that's just because that's where it fit best. The mccPBA generates epoxides. Once we've got the epoxide, we can then split off into two types of reactions. Acid catalyzed, H+, or base catalyzed, you'll notice the nucleophile is now negatively charged, so we get a strong nucleophile in the base catalyzed mechanism, generating slightly different products. Okay? We talked about the osmium tetroxide and the other thing there. I don't even remember how to say that. Hydrogen bisulfite. Anybody know how to say it? Then it's hydrogen bisulfite. Or permanganate. Both of those reagents do the same thing. We generate the syn addition or cis diol. Okay? So we're just trying to summarize all of those reactants as we go through. The last two that we talked about, hydrogen, adding hydrogen across the double bond. We put our hydrogens on. You'll notice I've specified the hydrogens as wedges here. We don't have to show hydrogen. Why might I add them in this structure? Why not just show what the actual product is in this case, which is just I'm trying to indicate as best as possible with a single structure what occurred in the reaction. Okay? The hydrogens were added on the same side. I can see that they were added on the same side. If we draw out what the actual product is, I can't see that. So the goal of these kind of flowcharts or these kind of spider diagrams is to keep all that information in there in a kind of a condensed as possible format. The last reaction that we evaluated with our alkenes was the bromine addition. You'll notice the bromines get added, and I put them on there showing the wedges and dashes again to show the relationship between those two bromines, okay, when you do that addition reaction. Okay. Last bit of information, okay, that wasn't covered in Chapter 5, because this whole bottom part is all the reactions of our alkenes, which was Chapter 5. The top part is our synthesis of alkenes. As far as you guys are concerned, we only have one synthesis so far. That is starting from our alkyl halides, and we're looking at elimination reactions, okay, be it E1 or E2. Once we move into Chapter 8, I'm going to add another synthesis type, okay? And in fact, at the end of today, I might even add yet another one, okay? Because we can get alkenes from alkynes, and we can also get them from alcohols, okay? So the idea is to put all that information in one spot that you can now quickly reference. What should you do with it? What's that?
Practice.
Okay, so you can practice with it, keep it handy so that when you go through and do the problems, if you don't know what particular reagents are because you don't have them memorized yet, you now have a quick reference. Say, oh, that does this. Okay? Even better, what you should be doing with it, turning these into note cards. Okay? Each of those reactions should get turned into note cards. We can then, that's not me, right? Okay. These can then be memorized because you're ultimately responsible for knowing those reagents. So you can either memorize them or the last thing that you could do, put them onto your cheat sheet. Okay? Let me reiterate with cheat sheets. Handwritten. If anything is computer generated, you will lose points on your next exam. Substantial amount of points. Okay? Greater than 10% of your grade. Okay? So the idea is that your exam is handwritten. If I make you handwrite a cheat sheet, it's partly building that muscle memory to help you memorize those reagents. Okay? That's why it's supposed to be handwritten. Okay? Questions about the spider diagram? Okay. Like I said, you will see these again and again. I will try my best before next Monday to see if I can't get the alcohol one put together so that we start with the alcohol one so you can actually see how painful it's going to be before we get into it. And then you'll see it at the end for sure. Okay. I guess one thing I can summarize here, you're responsible for the chemicals, so your reagents, what the products are, stereochemistry, which is ultimately your wedges and dashes, okay, and regiochemistry, which is a new, I didn't spell that right, is a new word. All that's referring to is where different atoms go. So the regiochemistry for the acid nucleophile reaction, the nucleophile goes to which, or the hydrogen goes to which position? In this double bond, where do you put the hydrogen? No one got the rule memorized? Should I draw out the reaction? Let's draw it out a little bit. Okay, so at least one of you's got it. Let's make sure everybody else has it. If I add HBr, what's the product? I put the hydrogen here. The intermediate has the positive charge there. So what we're referring to is for regiochemistry is that we only get one product. The hydrogen always goes to the position that has the most hydrogens. Okay, that's the regiochemistry. If the hydrogen went to both positions, we have no regiochemistry in the experiment. We'd have to predict all those products. Okay, so it's just a fancy way of saying we get one-ish product. Okay? As you move further down this line, you're moving into more and more difficult concepts. Those would be from the students that are more advanced, that are really pushing for a higher grade in the class. Okay? If you're just trying to barely get through reagents and products, you absolutely need to know. Okay? Questions about that? Okay. So, where's my mouse? I think probably one of the last things we'll talk about is alkyne reactivity. It's not in your textbook, so I'm not going to talk or spend a whole lot of time on it. I'm expecting you to manipulate a little bit as far as these slides go. When we look at the hybridization for these, we can look at orbital diagrams and we can see all that. For the alkene, what's our bond composition? We've got one, whoops, hey, now it's working. No, it's not. For our alkene, we have one sigma bond and one pi bond. For the alkyne, what do we have? One sigma and two pi. So any kind of reactivity that you expect for the alkene, we get that same type of chemistry for the alkyne. So if you want to do acid nucleophile reactions, okay, so adding HBr, we can add HBr to the alkyne. How many times would it add? HBr reacts with an alkene how many times? Once. What is it reacting with? The pi bond. Okay? If we move to an alkyne and I now react HBr, how many times would HBr react? Twice, because two pi bonds. Okay? So a lot of the chemistry mimics, you just end up doubling it through it. Okay? Oh, come on. Where alkyne chemistry really jumps out and becomes drastically different than your alkene or your alkane chemistry is the alkyne, because that carbon changes its hybridization. We've got what hybridization on that carbon? sp. It's become so S-like characteristic that it's holding the electrons really, really, really tight, which means that carbon is now increased in electronegativity so much that what happens to the electrons in the carbon-hydrogen bond? They start to get pulled towards the carbon, which means the alkyne can act as an acid. Okay? So given the proper conditions, i.e. we add a strong enough base, I can remove the hydrogen from the alkyne and I can make what's referred to as the acetylide ion. Okay? That is really synthetically useful, and in fact alkynes are probably the most useful functional group. Okay? Why is this synthetically useful? What can I do with a negative charge? I can react it with a positive. What types of positives are there? Hydrogens or pretty much any other atom. So I can turn a carbon into a nucleophile. This is the first case that we have a carbon as a nucleophile. We've never had a negative carbon in any of the chemistry that we've looked at so far. It's always been positive. When we decrease the hybridization enough, we can make that carbon electronegative enough to allow it to become a nucleophile. If it's a nucleophile, I can now do substitution chemistry with it. Okay? So it's kind of neat as far as functionality. Okay? So, come on. I've got a good strong base. Why is it a strong base? Does carbon want to be negative? No. So it's going to seek out something as positive as possible, as rapidly as it can. What's something that's typically positive? Hydrogen. So our acetylide ion can act as a good strong base. We've got a negative charge on that carbon, and it can't stabilize it that well. It's also a good nucleophile. Why is it a good nucleophile? Ultimately the same reason, it's negatively charged. Okay? Reactions with hydrogen or bromine, similar to the HBr concept. If we add hydrogen to the alkyne, how many times would we expect it to react? Twice, because the hydrogen reacts with pi bonds. How many pi bonds are there in our alkyne? 2. Okay? What type of reaction did I do to go from the alkyne to an alkane? Addition is fair, so I'm going to get rid of that answer. You can't say addition. Try again. Started at the very beginning. It's not technically substitution. We never removed an atom. Not really acid-base because you're not adding H+. Not an elimination. Reduction. We increase the number of hydrogen bonds in that reaction. Okay? We could also go through and react it with bromine. Okay? When we add Br2 across the alkyne, bromine reacts with a pi bond. If I got 2 pi bonds, I can put on 2 equivalents of bromine. So it can add twice. Okay? For those of you that liked balancing, how many of these reactions just shown are balanced? Absolutely none of them. Sorry. That's going to become increasingly irritating for you. I will try my best to balance things as best I can, but there's only so much I can do. Okay? Particularly if you look at your homework problems, you'll notice the homework is not going to balance even worse than I am. Okay? And that's mainly because it's organic chemistry. We're only concerned about the organic products. Okay? So the inorganic things we don't really care about. Bromine and hydrogen, both inorganic. What we're concerned about is that you know hydrogen reacts with a pi bond. Okay? Okay, we'll kind of end on, maybe to put it not nicely, depressing note. Moving into synthesis. Quiz, or that last quiz, question 10 was doing a synthesis. Okay? The intent of that was having you going through, and it labeled it out to identify all the reagents necessary and all the products. All of your products need to be neutral. Okay? They are not charged intermediates. They're neutral products. So what you have to go through and do is start working forwards and backwards. Synthesis almost always causes people the most problems. Okay? Mainly because most students don't have all the reactions memorized. So if you don't know what the reagents are, how can you possibly decide to break things apart? Okay? So you need to be familiar with the reagents to go through and attempt synthesis problems, otherwise you're not going to get anywhere. Okay? So this is a very similar concept, except made even worse, because I don't tell you how many steps there are to it. You just given the starting material and the product and ask to make it. Okay? So let's kind of go through and see what we can do with this in the next 5 minutes. Okay? Where should we start? Reactant or product? I heard reactant, so take a look at the reactant. When you look at that reactant, what functionality do you see? What reactivity? Okay, and now this one's going to be extra difficult because we just looked at alkyne reactivity. Okay, but we've got the pi bond. So we could do addition reactions. Addition reactions add two species, right? A positive and a negative. What are the types of reagents that we could add for addition reactions? We could do HBr. We can do Br2. We can do hydrogen. Okay, so there's a number of possible addition reagents we could do. We can go over and look to the product and say, oh, let's see what things have changed. Well, what things have changed? I've got a lot of bromines in there. And actually, I want to step that even further back. Before we decide what things have changed, we need to find out where our starting material is in our product. So where's the starting material? Let's go ahead and color it blue. Someone just say do it red.
It's on the right.
It's on the right. Where on the right? Yep. Okay. There's our starting material. Okay, and we even have the sigma bond in between. If we compare back things that are different, bromine, 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 and this big old carbon thing. Okay. Somehow or another, I have to get all of those pieces attached to this. Okay. Of those bonds, any of those bonds that you recognize might be easier to make or break than others? In the product. Let's go to the product first. You're right, the pi bond in our starting material is a good option. I'll mark 2 of them. How about in the product? Bromines sound reasonable. Okay, those are good, easy bonds to break. Why would they be easy bonds to break? Bromine is more electronegative than carbon. It's polarizing that bond. Anytime you've got a polar bond, you're looking at a site of reactivity. So putting those bromines on could be a relatively easy reaction to do. How could I add bromine to my starting material? If I add HBr, I'm going to add a bromine and hydrogen. If we compare starting material to products, do I add hydrogen? No. Okay, so HBr is out. I could add Br2. Okay, so we could say, oh, that's a good option. Let's go ahead and do that. Let's add Br2. What's the result? We could take it to the double bond between the carbons. Okay, if we got Br2, more than likely what's going to happen? What does that mean? Good or bad? Why you say good? True. Anybody say it's good for the reaction, for progressing forward? Okay, why do you say good? I agree. I think it looks good.
The carbons and the bromines are...
We've accounted for all of the bromines. We just put them all on our carbon. Absolutely, that looks good. Okay, what are we missing? Getting the ring. Okay, I intentionally didn't ask about this one. What bond is that? Carbon-carbon bond, which means for that bond to form, one of those carbons needs to be what charge? Positive, one needs to be negative. What charge is this carbon? Okay, neutral or at best partially positive. Okay. Further, let's say I bring in, let's say we magically make one. Let's just say it exists. Here we go. We've got it. Our negative carbon. Let's have that try and share its electrons with that carbon. What's wrong with that? Too many bonds on that carbon. We don't have enough places to put those electrons. So while it initially looks like a good idea, it's probably not the right time to do it. Okay? So it's something that we should say, you know what, probably we did that after we made that bond. So we could say over here, we probably added bromine to that compound. You guys see that?
Yeah.
The bromine has to react with the triple bond. And we said the bromines have to be added to our structure after we make the carbon-carbon bond. Okay? We haven't made that carbon-carbon bond yet. That's still going to be in this first process. Okay? Have we seen a way to get a carbon negative? What was that way? We add a strong base to our alkyne. This strong base removes that hydrogen, puts the electron density on that carbon, and I get a negatively charged carbon. Fantastic. I've got part of the puzzle because I was saying that that bond is not an easy bond to break, and I just made part of it. I made this carbon negative. So in this next step, what do I have to add? Do I have this piece? Do I see this piece drawn anywhere over here? No, which means, what do I need to add? This piece. Okay, so let's draw that piece in. Okay. What reactivity do I have in this compound? None. No partial charges. What partial charge does it need to have? It needs to be positive so that it can react with the negative. How can I get one of those atoms to be positive? I need to add a good leaving group. So let's add a bromine. What type of reaction occurred in this first step? That is your answer, by the way. We have an acid-base reaction. What happened in the second step? SN2, how do you know it's the 2 type, not the 1 type? No. Leaving group is secondary, or we got a secondary alkyl halide that says primary, or 1 and 2. Our nucleophile is strong, SN2. What happened in our last step? We've got an addition reaction. In fact, 2 times. Okay? Get the idea on how to process it. Get the idea why it's going to take a lot of practice to get through and do some of these. Okay? You have to be able to look for differences in reactivity, and that's ultimately what we started with. Okay? We need to identify what things changed as we moved from our reactant to our product. Once we've got those marked, we start to come up with ideas to see what happens. Bromine was the first one. We went through, drew out our product. We said, hey, we can't do anything with that. We're going to have to make our other bond first. So we just swapped the order. This is a relatively simple one. I don't think I'll ever test on anything longer than this. Okay? 3 steps. Okay? I'll go ahead and stop. I mean, just because I guess I feel like it.